In today's lesson, I'm going to take you through Belman-Ford's algorithm, give you a high-level explanation about Belman-Ford's algorithm, show you the steps as to how to use and implement Belman-Ford's algorithm, and then take you through an example and show you the fastest way of how you can implement Belman-Ford's algorithm on the example that I have at hand. So Belman-Ford's algorithm has the same results as Dijkstra's algorithm. If you have not checked out my video on Dijkstra's algorithm, please go ahead and check that video out. It has a lot of explanation and quite a detailed examples of using and implementing Dijkstra's algorithm. But coming back to Belman-Ford's algorithm, it is similar to Dijkstra's algorithm, where we want to find the shortest path from one of the nodes in the graph to the other nodes in the graph. The main difference with Belman-Ford's algorithm is, firstly, it is not a greedy algorithm compared to Dijkstra's algorithm, which is a greedy algorithm. But most importantly, Belman-Ford's algorithm can work on graphs with negative edge weights, where Dijkstra's algorithm cannot do this. So that's basically what Belman-Ford's algorithm is, and whenever you see or have some negative weights or edge weights, that will give you a hint that you need to use Belman-Ford's algorithm instead of Dijkstra's algorithm. So let's go ahead and look at the steps to implement Belman-Ford's algorithm. Now, the first step is very similar to Dijkstra's algorithm, where we need to ensure that we have, so number one is to have or set all your nodes to positive infinity. So that's step one. If you recall from Dijkstra's algorithm, we also do that. And we also do the second step, where we set the starting node, to 0, because the distance between yourself is 0. Okay? Then we go ahead. So the third step is to go ahead and update each of the edges, and we iterate through this v minus 1 times, okay, where v is equal to your edges or your vertices. Let's actually call this vertices. Okay, I will show you an example shortly on what I mean with that, and then we constantly repeat until we find the best cost for each of the nodes, or the best distance for each of the nodes. Now, one thing to take note of in Belman-Ford's algorithm is that we do not need to follow any specific order. So if you have node A, B, C, D, you do not need to go from A, B, C, D. You can actually go A, C, D, B. So that's something very important to take note of, mainly because it might confuse you depending on the graph that you get, that you might be looking to actually perform these steps in order of the nodes itself. Okay, so just take note of that. So let's say, for an example, we have nodes P, or city P, city A, city B, C, D, and you have your weights between them as 3, 5, minus 2, and 1. Okay, now, like I was saying in the steps, right, we need to find the shortest path, maybe from B to D, but we need to emphasize that we, in this case, will iterate a maximum of 4 times. Okay, so this is a guide that you need to remember, that you will go through an iteration of vertices v minus 1 always. Okay, so you have 1, 2, 3, 4, 5 vertices. So v minus 1 will be 4. So that's how we got our 4 vertices. So always ensure that it's v minus 1 or the number of vertices minus 1 from the starting node to any other node. That's how you are going to ensure that you're working on this correctly. The other thing that you need to note, right, is when you are looking at this in terms of the vertices, so if you do come across v or more edges, okay, so if you do come across a v or more edges, then it means that you have a cycle. It means you have a cycle or a repeated edge. Okay, so just take note of that, right? I'm not going to go into too much detail of this. This is I just want to get to the point where I can show you how to actually implement this algorithm so you can go ahead and do that in any question that you do get. But this is something to note. Ensure that you iterate for a maximum of v minus 1 iterations, and if you are iterating v times or v plus 1 or v plus n, it then means you have a cycle or a repeated edge within your graph. Okay, so that's basically the high level theory I wanted to take you through. Next up, I'm going to take you through an example and show you how you can implement Bellman's algorithm extremely quickly. Also, you probably use this in any question that you get, and identify. Once you use Belman's algorithm, you can use the hints that I'm going to show you up next to quickly solve the problem and giving you more or extra time to work on other problems that you have in your exam or in your test. Okay, so let's look at this example, right? Just feel free to pause the video and take down the graph on the left of the screen here so we can work on it together. So we have nodes P, E, A, D, F, B, and you can see the weights in between. You can also see there's negative weights here as well. So that means we will need to go ahead and use Belman-Ford's algorithm. Now, the first step that I want you to do, and this is the first hint that I'm going to give you, is go ahead and jot down or note down all of the vertices or all of the edges that you can find. So we can find the first edge as PE. So we can say we have PE. Then we have PA. So we can say we have PA. Then we have ED. ED. Ensure when you're doing this that you follow your arrows, right? So don't do it the opposite direction. So we have ED, then we can have DA going in that direction, DA going that direction. We can then have D and DC going down here. Just one change we need to make to this graph. This should actually be C because we're missing C. Okay, so this would be DC. Okay, then we'll have AC here, so AC. Then we'll have CB, so CB here, CB, and then we'll have finally BA. BA. Okay, so that is all of the vertices that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8 vertices for this graph. Now if we count the vertices, 1, 2, 3, 4, 5, 6, we have 6 vertices, right? So our V here is equal to 6, meaning that we should not go greater than 6 in terms of the number of iterations we are going to have. So if you come to the table on the right that I have here, so this is just my way of showing or representing how we're going to work it. You could find a different way or have your own method of doing this, but I noted down all of the vertices on all of the nodes here on the left, and then in the table for each iteration, we are going to then put in the weighting or the shortest path to that specific node from our start point P. So let's go ahead and start looking at this, right? Before we do anything, we know the first rule is we make our start point 0, we make everything else infinity. Okay, so everything else is infinity. Once we're done with that, we now are going to look at this for each of the vertices that you will now see. So using this graph here, right, or this direction that we have here, we are first going to look at PE. So we know this will still remain as 0. Then we're going to look at PE. So PE tells us that when we use PE, we're now going to have that weighting as firstly 8. So this would be 8. Okay. Then we are going to look at PA. So sorry, this is actually incorrect. This is PE. Right, so PE is 8. Okay, then PA is 10. We can see we here, so PA is now 10. So we're done with P. We then going to look at E, the E and the D's. So E to D is 1. However, we know that E is already 8, so 8 plus 1 is 9. So ED, so D will now become 9. Okay, so ED is done. Then we can look at D to A. So D to A here, the weighting is minus 4. We already know that D is 9, so 9 minus 4 is 5. Okay, so we can see that A was 10 here previously. Now 5 is smaller than 10, so we're going to replace that with 5. Okay, then we're done with DA. Then we can do DC, right? So the weighting between D and C is minus 1. Okay, but however D is 9, so 9 minus 1 is 8. So C is now 8. Okay, then we are done with DC. Okay, then we can do AC. So between A and C, so A is currently 5. The weighting between A and C is 2, which 5 plus 2 is 7, which then gives you a smaller value than 8. So we can change 8 to actually 7. Okay, following me so far? So we are now done with AC. We're now going to look at CB, right? So CB is here. We know that C is 7. So 7 minus we know that C is 7. 7 minus 2 is 5. So this is now 5. And finally, we're going to look at BA, right? We know that B is 5. We know B is 5 plus 1 is 6. 6 is greater than 5 already, so we are done with that iteration. We just need to get rid of this here. Okay, so we are done with that iteration. So first iteration done. Let's look at the next iteration. Okay, so looking at the next iteration, we followed this vertices pattern again. Now you can see how easy it is, right? If we can write down or jot down the vertices and just follow the vertices, it will immediately be able to help you get to the answer quite fast, right? So we can already see we are already getting the shortest paths here at the moment, and you can also see it's not a greedy algorithm, right? It's not taking us too long to get to the shorter paths right here. You can already see we got 5, we got a 5 here as well. So let's go ahead and now follow this again. So for iteration 2, we look at P and E again. PE, we see we cannot get any shorter path in this, so we're gonna leave E as 8. Then we have PA. So we have PA here. We see PA is 10. However, A at the moment is 5. So we are not going to make any changes there. We are going to leave this as 5. Don't forget the 0 here by P. So we're done with that. We're done with this. We're going to look at ED, right? So now if you look at E and D, so ED here is 1. So E is currently 8. 8 plus 1 is 9. D is already 9, so we're going to leave it as is. No changes there. Then we're going to look at D and A. So we're going to look at D here to A there. We know D is 9. 9 minus 4 is 5. We already have 5. No changes to A. Then we look at D and C. So if you look at D and C here, so D and C here is -1. We know that D is D is 9. 9 minus 1 is actually 8. So C is already 7, so it's higher. We do not make any changes there. Then we're done with DC. We're going to look at AC. So AC is here. It's 2. As the weighting, A is 5 plus 2 is 7. C remains as 7. CB, then we got CB here. So C and B, we got -2. C is currently 7. 7 minus 2 is 5. B is already 5. We're going to leave it as 5. And then finally, we have BA here, which is basically this path right here, which is 1. B is 5. 5 plus 1 is 6. We do not make any changes. Okay, so as you can see, the second iteration gave us back what the first iteration gave, meaning that we have already found the shortest path in the first iteration. So this is our final answer right here. So coming back to basics, we said we should not iterate more than v minus 1. We have iterated less than v. We have currently iterated less than v minus 1, which means that we are good with the Bellman's algorithm, Belman-Ford algorithm, and we were able to find this actually in the first iteration. I did it in the second iteration as well, just to show you that we are going to get the same answer, but at the same time showing you how to iterate. So as long as you write this vertices down, this is how you would always iterate. Okay, so write this down, jot it down, have it with you, because this is how you would iterate for each iteration until you get to the point of this scenario that we just had here. When you iterate again, you're getting the same values as the previous iteration. So we were actually able to find and iterate through this graph using Belman-Ford's algorithm extremely quickly, and we were able to find this value out by the first and second iteration. So this is basically how you go ahead and use Belman-Ford's algorithm. My main hint is write down this vertices for each of them. It'll take you a minute or so. Use this as a guide to then go through the iteration. You will continuously go through and cycle through these vertices until you find the shortest path. But at the same time, keep in mind that you should not go v minus 1 iterations. If you are going more than v minus 1 iterations, like mentioned earlier, you probably have a repeated node or a cycle in your graph, which is an exceptional case. But if you are going beyond that, then you already know that you are doing something incorrect. So please stop at that point and have a look at what you've been doing. Similar to Dijkstra's algorithm, start node is 0, everything else is infinity. Ensure that the weightings or the shortest distance that you're putting between the nodes are always smaller than your previous values. Do not put anything higher, as you saw here when we had 6 for A, but we already had 5. We did not replace the 5 with the 6. We want to find the shortest path first. So that is basically Belman-Ford's algorithm to find the shortest path. Quite simple. It's quite shorter than Dijkstra's algorithm, and you can actually see why Dijkstra's algorithm is called the greedy algorithm. It does take you a bit more time to actually go ahead and find the shortest path with Dijkstra's algorithm. Dijkstra's algorithm does not work with negative weights. So once you see negative weights in your graph, you should already know that you need to use Belman-Ford's if you are requested to choose between Belman-Ford's and Dijkstra's algorithms only. So you already know you need to use Belman-Ford's in this example. And then go ahead and write the vertices, draw your graph, and always ensure that you do not go more. I'm keep on stressing this, but don't go more than your v minus 1 vertices in terms of your iterations or your relaxations. But always keep that in mind, because that's how you will be able to check your work. Because this, you could get more complicated graphs than this that could take you longer than what I showed you here, and that would waste time if you need to go back and actually check your work after you have completed everything. So go ahead, use this method. It would work for yourself. Have the vertices in front of you, jot it down. You won't get marks for it, but jot it down. Keep it in this keep it on the side of the question or on your answer sheet, so you are able to follow the repetitive or the iterations through each of the edges. So that is it for Bellman's algorithm. I will look at uploading more videos around this or more examples, but ensure that you like and subscribe, and I will see you in the next video.